Hello, my name is Jesse Schottner, and I am doing a video for the XFL R5 final project for Fundamentals of Aerodynamics with Dr. Osbey. My two other group members are doing the mandatory parts of the project, so they're doing the XFL R5 stuff. I am doing the bonus simulation of the Fluent simulation around an airfoil in Ansys. So I'll be going through designing it, creating the CAD, putting in the Ansys, and getting the values we need. So just like the XFRL, XFL-R5 part of the project, we're using a NACA 2415 airfoil. And what I used to get those points to create in the CAD is I went to Airfoil Tools, Airfoil Plotter, and as you can see we have our NACA 2415 airfoil. And what I did is I set my chord length to 1 meter or 1,000 millimeters. And when I clicked CSV file coordinates, that gave me the coordinates of all these points, which allowed me to create the spline of the airfoil. So if we go into Inventor, as you can see, we have the sketch that I made. I'm not going to do it again, but just to kind of show how to do it, you go to Points, you click on one of these, and that will create these points you see here, and then you just create the spline around it. Again, I'm not going to do it because it's pretty straightforward. It just takes a little bit of time. And then I created my box around, which is about 4 by 3 meters. And as you can see here, I sketched out the surface and made the airfoil surface first, and then I cut it out into 6 sections. And the reason I cut it out into 6 sections is I cut it out at the leading edge and the trailing edge is for the mesh. So I'm not going to go through how I did all this because it's just an Inventor. You can do this in Ansys as well. But again, the reasoning for this is so we can get a good mesh. So we're going to go into Workbench. As you can see, I already have some of these here. We're going to open a new fluid flow tutorial. And we're going to show how I did it here. So we're going to import geometry, and let me just make sure. Which one did I choose? I believe it is final. Yeah, it took a lot of iterations with the mesh, but I was able to get something good. So we got our geometry in there. I'm going to open our mesh. So I will go through the mesh process. This took me quite a bit of time, but you want to have a really good mesh, especially for an airfoil, because it's not as simple as a flow over a cylinder or whatnot, and you can get a lot of different changes depending on your angles and whatnot. So we have our mesh here. So first thing we're going to do is create our named selections. So everything here in the front is going to be the inlet. The back here is going to be the outlet. And then these will be just symmetry, so it knows these aren't walls. And then we have our airfoil. So this is what the issue was, is my airfoil is not just these two pieces. As you can see, if I zoom in, very, very slight zoom in, there is a bit of the edge that intersects in this other section. And that was the reason my mesh wasn't great. Now, you're never really going to get it fully on the trailing edge. You can probably try and do it, but it's a little difficult. So it's okay because I was still able to get good results with this. But there's a lot of different ways you can do this mesh. Most people will do the grid like this. Some will do a cylinder or semicircle in the front, which helps with this little airfoil section expanding. But this works just as well. So this is going to be our airfoil. And now we have our name selection. So first thing we're going to do is we're going to create a method, and we're going to select the entire thing, each category, apply. I don't know how to do it. And we're going to click generate. And that's just going to create our quadrilateral dominant, and we need that to do the rest. So now we're going to go to our sizing. So we're going to do a lot of sizings here. First sizing we're going to do is these 3 here, and these are going to be number of divisions, and we're going to do 150. And what this is going to do, click no. We're going to do soft behavior and not blend. This is going to have a bias, and it's going to be a bias factor of about, I want to say, let me double check really quick. Yeah, so that's going to be 250 divisions and a bias factor of 100. And what that's going to do is it's going to move our cells from higher size to lower size as it gets closer. We need to do a reverse bias on these three. Cool. So as you can see, the cells get bigger here and they get smaller here, as that's where we need the finer mesh. So that is our first edge sizing. We're going to create another one that selects these three in the back. These are going to be the exact same number of divisions. The type is the number of divisions, but they're not going to be the same number. It's going to be only 150. Get rid of capture curvature. We're going to make that a hard behavior and not blend to neighbors. We have another mesh or sizing we're going to do, and that's going to be for these in the front. You could group some of these together, but it doesn't really matter realistically. So we're going to apply these. This is going to be the same thing actually. 150. Click no, no bias, capture curvature, and make that a hard behavior. Cool. So now we have 3 of our edges. We're going to need 3 more. Again, it depends on how you section this out. We're going to do everything here in the middle. We're not going to include those little ones because this is going to be another number of divisions. So if we go here and we click type the number of divisions again, we'll do 150. As you can see, they're all pretty even in terms of like there being 150 around across the entire line. If I were to choose one of those smaller parts, then that small line, which is about like 1 millimeter on the back end, would have 150 divisions and it would just destroy the whole thing. So we're going to do this and then we're good. So now we're going to do the sizing for those small ones. So we're going to go to the front here, and what I found that worked best is we're going to do, click this. We're going to keep a number of divisions, but we're only going to do 10. This is going to be pretty small, but compared to the other divisions, it actually turns out to look pretty nice. And we're going to do no blended behaviors, no bias, and a hard behavior. Now the back one is a little different because it is so minuscule that the cell itself is probably around half a millimeter. As you can see here, it's very small. About half, not even, probably more, probably less than that, so probably like 1/10 of a millimeter. So what we're going to do is we're going to go to mesh, we're going to click insert, sizing once again, we're going to click this one in the bend, geometry, and we're going to keep it at element size. We're going to keep it at that, and everything else is fine. Don't want to blend the neighbors, no capture curvature, but it doesn't really matter because it's not going to be divisions. And now element size is 0.25. Yeah, we don't want that. We want to make our element size 0.015. Yeah, so we're going to make that 0.015 for our element size. And we're going to click generate. And this is going to take a second. So I will pause and come back when it's done. Okay, so this is the mesh I got. And as you can see, it's not exactly what we want. And that's because I did the wrong thing for this. This should not be an automatic method. This should be a face mesh to help map the entire thing and identify each as quadrilaterals. So now we're going to generate it and we're going to give it a second. Alright, so as we can see, our mesh is a little better. We ended up getting some symmetricals here, but there's still some issues with these 3 sections, and what we're going to do to fix that is this one, I forgot to add these back ones as well, so we're going to click apply. And we're going to do another reverse bias here, and that just helps with the symmetry at the back there. 150, 150. We're going to switch this to 125, and then we're going to go, that's good, and that should be good. I'm also going to change the sizing to 0.008. We're going to make it a half bit smaller. We're going to generate that, and we'll give it a second. And it actually took like 1 second to do. I could generate that again, but yeah, that literally took 3 seconds to fix. And as you can see, we have a beautiful symmetrical grid that gets much finer here. Now sometimes you might not want this because this, it might be too fine, but this looks very good for what we want. The cells get smaller as we get closer to where the fluid interacts with the surface, and it gets bigger as it goes outward. And in terms of statistics, it's about 100,000 nodes. Nothing crazy. You don't really need that much. It's not that big of an area as well. So, as we're done with our mesh, we've now shown the process of creating it, the mesh. We're going to go into the Fluent solver itself, and we're going to show how to get our values. We're going to update this as well. Give it a second. Cool. So the mesh is good. We're going to go to Setup, open our Fluent solver, double precision, 4 processes, the max you can do for the student version, and we're going to open that. So what we're going to use with Fluent is we have an air density of 1.2 kilograms per meter cubed and a viscosity of 1.8 to the power of -5 Pascal seconds. Very normal for air. And the Reynolds number we want to achieve is 1 million. So the velocity that I have calculated with the chord length of 1 as well as our length will be 15 meters a second. And for this, I'm going to show, I'll show the 0 degree and the 10 degree analysis. I know the project asks from -3 to 21 degrees from increments of 3s, but once you do a angle change, it's the same thing basically over and over again. So, yep, I'll show you how to get those plots as well after. But let's begin. So we're going to go to, we're going to use Spilart for this. I ended up using K epsilon for the higher angles due to getting closer to stall and the flow acting a little more strange from around 15 to 21. But for these smaller degrees, the one equation Spilart al Maras, I don't know if I said that right, will be okay. So we're going to click OK on that. We're going to go to materials. And this should be pretty similar, but just in case, 1.2 and 1.8 -5. Change and create. Let me actually go back to models really quick. Yeah, that looks good. Materials will be good. Cell zone, make sure that's air. Splendid. And now we're going to go to our inlet. So our inlet is just going to be 15 meters per second. This is the 0 angle of attack. You will see what I change to make it 10 degrees after this one. So we're going to click apply, click close. Everything else looks good. Eternal wall looking sweet. Reference frames all looking good. And now we go to report definition. So we're going to do 2 reports here. One for drag coefficient. We'll name that drag coefficient. And everything else stays the same. Click that for airfoil. Click OK. Close. Do the same exact thing for lift. Lift coefficient on the airfoil. Beautiful. And now we have those. We're going to go to our monitors, change our residuals to much lower values so they converge at better results. And that should be good. So we're going to initialize this here. Initialization is done. Give this a second to load. Alright, that initialization is done. We're going to go to run calculation. We're going to do 1,000 iterations. It should definitely converge before this. And again, the reasoning I'm doing 0 and 10 is because the project itself asks for contours of velocity and pressure only for those 2 angles of attack. And again, once you do one angle change, you can get the rest pretty easily. Alright, let's click calculate, and we'll give that a second to start. Alright, so our sim is running, and as you can see, our values are converging very nicely, and it's already done. Amazing. So now we have, hold on, maybe just open Excel really quick. Now we have our drag and lift coefficients. Just give me 1 second. This is loading. Cool, so calculation complete. We're going to click OK. And we're going to go to our drag and lift. And we can see that's interesting. Okay, so as you can see, I was messing around with the contours. The contours look good. My drag and my lift are way off. My CL should not be, as you can see, above 40. That's insane. The reasoning is because reference values, I forgot to reference the inlet. Now our viscosities and velocities change. So we are going to initialize this and lose all that data because that made no sense when I saw it, and I'm like, that's not what I got before. So I'm going to initialize this, I'm going to run it again, and I will see you in 1 second. Calculations running, and as we can see, our lift and drag make much more sense. Our velocity before was at 1 meter, which really just messes up the whole Reynolds number. But as you can see, much nicer, and it converged. And it needs a second to load. Calculation complete. Let's go to our drag coefficient. We're going to compute that. Looks much nicer. Go to lift. Much nicer. Cool. So our CD and CL give us pretty fair numbers. Our drag should not be that high at 0 degrees. Our lift should be pretty low, all things considered. There's some high pressure on the bottom. Realistically, that CL should... Actually, realistically, that CL is good. The CD should probably be a little less if we compare it to our NACA airfoils. I'll show that in a second with those plots. But it's pretty solid. And now we're going to show the 10-degree one. Oh, I'll also show the contours. Velocity contour makes sense. You got your stagnation point here. You got some flow separation here as well with this wake region. So, makes sense. Higher pressure and a higher velocity, more red on the top than the bottom, but it's still pretty even. But you'll see how this changes with the other ones. I'm also going to show the pressure. And we're going to show the static pressure. And as you can see, high pressure on the top, low pressure on the bottom, but not as crazy. And I'll show you what I got before as well. So now the last part, well, not the last one, the last Fluent part is we're going to do it at 10 degrees. Now the way to change it to 10 degrees is very easy. You just have to use geometry. So we're going to go here and do magnitude and direction. So it's basically just the velocity components of your free stream in the x and y. So for x, you're doing free stream velocity times cos theta. The y is free stream velocity times sine theta. And we got this calculations right here. So we're just plugging in that x component, which is that cos theta, which is cos 10, cos 10, which will be 0.984808. And we're going to do our y, which is going to be 0.173648. Now I'll give you your x and y component for your velocity. Drag is going to be the exact same thing because drag is along that same direction. It goes from left to right. And we're going to do same numbers, 0.984808. And this is going to be 0.173648. And we'll copy that. Click OK. Now the lift is interesting because you're rotating in 90 degrees, and if you do the geometry of the triangle, you're flipping your x and y's, and your x has to be negative because, again, you're adding 90, so you're going into the second quadrant on an xy graph. Again, the geometry proves it. So our x is now going to be negative of our y, and our y is going to be our positive of our x. And we're going to click OK. And we don't have to initialize it again because it's everything's the same. We just changed the velocity inlet. So instead of going like this, it will technically go kind of like at an angle. Cool. So we don't have to initialize again. Click Run Calculations, and that's okay. And give that a second to load. All right, the calculation starts. And as you can see, it kind of messes with our other values, but it doesn't really matter for this point. But if you look to our drag and lift, you can see, I'm pretty sure this just crashed on me. As you can see, there was a spike. Well, yeah, there was a spike. But hopefully this comes back. Give it a second. Cool. So it looks like it stopped, but it still needs a second to run. But it definitely did converge. So give it 1 second again. Okay. Calculation complete. You can see it converged. The drag and the lifts spiked. That makes sense. You know, as your angle of attack increases, your drag increases, and your lift increases, obviously you get to the point where stall happens. But if we go to our drag and we compute our drag and our lift have both increased very heavily. Our lift went from 0.19 to 0.45, and our drag went from 0.013 to 0.067. No joke intended. And yeah, that's pretty much the overall gist. If you want to do your increments of 3 from -3 to 21, you would just change those XY components in terms of your cosine and sine values. And now I will show how I plotted those on Excel. So I just got that for every value at those angles of attack. And here is the Excel sheet, which we will submit. CL increases, CD increases. Here are your contours. I guess I'll show that. Here's your contour of your static pressure. As you can see, low pressure remains on the top. Much higher pressure on the bottom compared to what we had for the 0 degree angle of attack. And if we go to velocity, it's the same idea. Much higher velocity on the top than the bottom. And if you look at those differences, the shaded in from the bottoms of each are much different. And here are our graphs compared to everything else. Definitely some differences, but the trends follow the same idea. Definitely could do a better mesh, could do a better model, but yeah, that's how you plotted the graphs in Excel. I don't think I really need to show how to plot them. I just copied them here and created these plots, and yeah, that's pretty much all there is to it. Thank you very much.